In this video, we want to learn about something super cool, I think. They're called colligative properties. Now, a colligative property is kind of a weird thing, right? It is a property that depends on how much is dissolved, but not what is dissolved. Now, let's talk about applications that you are probably somewhat familiar with. You know, if you live in the north, this wouldn't be true in Houston, but let's say you live in Chicago where there's snow all the time. And you know what they do in the winter? They pour boatloads of salt on the roads. Why? Why do they pour salt on the roads? Because they don't want people to die and their cars skid off the road in the wintertime. Let's talk about why that is. Now, you probably know this, is that water freezes at 0 degrees Celsius. So if it gets below 0, you could have ice on the roads. It's very bad. And what they do is they put the salt in the water, and something really interesting happens, is that instead of the water freezing at 0 degrees, it freezes at a lower temperature. So it might freeze at, say, minus 10 degrees Celsius. Now, that's like 0 Fahrenheit. Meaning that the ice, it can get colder and colder and colder, and it's still wet. And you're driving through like slush, even though the road is less than, it's a liquid at a lower than 0. Now, how is that possible? Because, turns out, there are 3 key colligative properties. The first one, which relates to this, is called freezing point depression. So if you add a solute to a solvent, it lowers the freezing point, hence from 0 to minus 10. The second one is actually kind of opposite. It's called boiling point elevation. Now, water, as you probably are aware, boils at 100 degrees Celsius, 212 Fahrenheit. And if I add salt or whatever, some other chemical, doesn't have to be salt, any substance, right, depends on how much it is, you can raise the boiling point to maybe 120 degrees or something like that, and then it will boil at a higher temperature. Now, there's actually a very interesting application that you may or may not know about. In your car, your automobile, there is a radiator, and the radiator cools the car. Now, and they fill the radiator with a fluid called ethylene glycol. It's actually ethylene glycol in water. And because it raises the boiling point, as the car gets super hot, above 100 degrees, it doesn't boil the liquid, because if it boils the liquid, it'll explode your radiator. Bad, right? And so you can actually have it at a higher temperature. And by the way, it's also sometimes called antifreeze, because it also has a lower temperature. So antifreeze might go from, say, 150 degrees, now this is Celsius, down to minus 15 degrees Celsius. And then when it's super cold, right, it doesn't freeze, expand, break your radiator, and it doesn't boil away when the engine's hot, either on a summer day or just hot because the engine itself is running. So a lot of interesting things. And there's a third one, as it turns out, and the third one is actually the cause of the other. It's called vapor pressure lowering. Now, this is intriguing. I'm going to draw a graph. You may not be familiar with this, but there's a graph of pressure versus temperature of every chemical in the world. So let's just, water is a good one example. And it looks like this, where if you have it a particular pressure, let's say at 1 atmosphere of pressure, as you heat it up, this would be at, say, 1 atmosphere of pressure, so it's sea level, that this temperature, if this was water, would be 100 degrees. Means that at 1 atmosphere of pressure, all right, as you heat it up, it will boil at 100 degrees. Okay? Now, vapor pressure lowering, and by the way, the vapor pressure is the pressure of a liquid as it evaporates. And you know this. If you're in a shower, a hot shower, there's more steam, so it has a higher vapor pressure. If it's a cold shower, there's less steam. Right? Has to do with the temperature, gives you the vapor pressure. I could find the temperature on this graph. Let's say I've got water here, then the vapor pressure would be this much. And if it's super hot water, it's actually just going to boil. All right? And what happens is, because of the solvent, so this is pure water right here. This line is pure water, or pure chemical, could be any pure chemical. And then this one would be a solution. And so what it does is it lowers the vapor pressure a certain amount. And the reason it does that, and this is awesome, I think, is because of forces of attraction. So if I have a beaker filled with some solvent, we'll have it be this color, and then I've got, I'll say X's are my solutes, and actually just have another beaker just filled with the circles, if you will. You see, for this to evaporate, all it has to do is break the bonds from this to this. But if you're having to, of their interactions, when you've got the X and the dots, if you will, there's attractive forces here, and they want to evaporate. And since they want to evaporate, but there's additional forces, not just, you don't have to just break the bonds between the dots and the dots, but between the dots and the X's, as I've drawn it. And that's why it lowers the vapor pressure, which actually lowers the freezing point and also raises the boiling point. So actually vapor pressure is what causes freezing point depression and boiling point elevation. And the two applications we talked about are cars and also salt in the roads. If you live in the northern part of the United States or any cold place, you could be living in southern New Zealand and they might put salt on the road. Same idea. And actually one other application that you may have played around with, I don't know if you've ever done this, but if you're making homemade ice cream, do you know what you do? So you got a can and then you put the ice cream in this container, and over here you put what? You put ice. But not just ice, you also put salt, because ice cream does not melt, or freeze, pardon me, at 0 degrees. It melts at something less, so this lowers the temperature and allows this stuff the ice cream to freeze. So colligative properties, an awesome, really cool chemistry thing.